Scalar valued functions take a scalar as an input and output a scalar. So in this example, the point here is described by two scalar functions. Now in contrast, a vector valued function takes a scalar as an input and outputs a vector. And here is an example of a special type of vector known as the position vector, which is measured from the origin, and that vector gives the location of that point. So what we do is add the horizontal dimension, which is x, and x equals f of t, and we multiply this by the unit vector I, which gives the direction along the x-axis. So I has a magnitude or length of 1. And similarly in the vertical direction, we multiply the y-coordinate of the point, which is given by g of t, by the unit vector in the vertical direction. And you can observe this visually over here. So effectively drawing the position vector along the curve in this interval traces out that curve. And we'll see that in an example. We can extend the methods for differentiating real or scalar valued functions to vector valued functions. So suppose we have the vector valued function that takes an input t, and that gives the following position vector. Well, similarly, we can write r at t plus delta t as follows. And using vector addition, we can obtain a relationship between r at t plus delta t and r of t. Where delta r is the secant vector between 2 points along the curve. And rearranging this equation, and dividing through by delta t. And now if you take the limit from both sides, as delta t approaches 0, we get the derivative of r with respect to t. And I encourage you to make these substitutions and use the rules for limits, and you'll be able to write the derivative as follows. And now if you differentiate this first derivative, you'd obtain a second derivative in the following form. And note that when we differentiate, the unit vectors I and j do not change magnitude or direction, so they just remain constant. Let's plot the curve traced out by this vector valued function. So x of t is equal to t, and y of t is equal to 1 minus t squared. So what we'll get are the following values from t equals minus 1 to 2. And now we can draw vectors from the origin to these points. So the first point is at minus 1, 0, 0, 1, 1, 0, and 2 minus 3. So basically our curve is going to look something like this. So we plotted the curve described by this vector valued function, which is a parabola, from minus 1 to 2. from t equals -1 to 2. And now we're asked to find the tangent to the curve described by the following vector valued function when t equals 1. So if we differentiate this vector valued function, we obtain the horizontal unit vector minus 2t by the vertical unit vector. And when t equals 1, we obtain I minus 2j. So as we can see, when t equals 1, we're looking at the point 1, 0. So the tangent vector is going to look something like this. So for every 1 unit in the horizontal direction, the vector goes down 2 units in the vertical direction. So in other words, the slope is minus 2, which makes sense. Given the same vector valued function we plotted previously, we now want to verify that the point xy, when t equals 0, is a minimum. So if we differentiate this vector valued function, we'd obtain the horizontal unit vector minus 2t by the vertical unit vector. And if we differentiate again, the second derivative of r with respect to t is going to give you minus 2 by the vertical unit vector. So when t equals 0, which is described by this point at 0, 1, we can see that the tangent vector described by the derivative is in the horizontal direction, and the vector of the second derivative points downwards at this point. So because this vector points downwards, then this point is not a minimum, it's actually a maximum. Given the vector valued function that we plotted earlier, let's determine an equivalent real valued function y of x. Well, as we can see, x of t is equal to t, and y of t is equal to 1 minus t squared. So therefore we can write y as a function of x by substituting for t. So that's effectively 1 minus x squared, and that gives the function of this same parabola over here.